Okay, I think we should probably try and make a start to this, given that we're officially meant to be starting at 2 o'clock and so forth. So before I start on the whole tutorial thing, just sort of some housekeeping reminder things and so forth. What were they? Because we're scattered all around this hotel, the actual break is going to be brought in here at the side. So you see it's kind of partially set up. So you don't need to go rushing out looking for the break at 3:30 because it is actually going to come in here. And obviously, if you don't want to stay at this tutorial, you want to go somewhere else, then go and look for the other break wherever it's being held. Then at 5:30, we've got the community meeting. Encourage you to come to that if you're interested in NANOG and the future and community stuff in general relating to NANOG. So that's in, where is it, in the Emerald Room. The Emerald Room is all the way at the other end of the hotel. So you go back out left, up the stairs, and all the way along to the end of the foyer. So that runs from 5:30 to 6:30. Then we've got the Switch and Data social event tonight. It's a welcome party. That starts at 7 o'clock. And that's going to be at the Bonaventure Brewing Company, which is about 3 blocks from this hotel. They have maps of how to get there at the registration desk. So if you want to go to the welcome party, please do, and pick up your map. Another thing I should mention, those of you who have been to NANOG before, note that every October NANOG we have elections for the steering committee, and we usually have some charter changes. So this year is no different. We have 7 candidates up for election to the steering committee. I sent an email to NANOG Announce a few minutes ago, but if you aren't reading email, please have a look at the elections website and check out the charter changes and the steering committee candidates as well. So those are the items of business before I get going here. So I think we can make a start to this. So this is BGP techniques for service providers. Generally a partly introduction, reminder, recap of BGP and how that functions, plus looking at some of the issues that are facing internet service providers today. So it's basically in 2 sections. The first section is a little bit more of really what BGP is, a bit of recap and so forth. And the second one, I tend to look a little bit more at like good practices and how you do general configuration peering and so forth with other providers on the network. So those are the 2 general pieces I want to look at. So the break will be somewhere in the middle. I don't know. I'll keep talking pretty much until 3:30, the break time. And then, so we'll pretty much see where we get. What else? I'm Philip Smith, as it says on the slides there. I've been doing these tutorials for a few years now. So this is part of a series of 3 that I do for NANOG and other network operations group events. So this is kind of the intro deployment version. Also, there's a multi-homing tutorial that goes along with this and a troubleshooting tutorial that goes along with this. So if you have a look back through the NANOG previous meetings, you'll see examples of the tutorials I did then if you're interested, if any of you are new to any of this. Presentation slides haven't actually made it on the NANOG website yet because I haven't actually given them to anybody at Merit. But they will do probably by the end of the day. But I have got them up on my own site there, available FTP. So if you want to go and grab them and follow the slides through as I'm speaking, feel free to do that. As I say, they will be on the NANOG website eventually, hopefully by the end of the day. Feel free to ask questions anytime. The session is being recorded at least. Yes, it is being recorded. So if you want to ask a question, I'd rather you use the microphone, which is standing in the middle of the room, because that way I don't have to repeat the question for the rest of you to hear or for the recorded listeners to hear it. So please, if you would like to ask questions, please use the mic. Right. Okay, I think we're pretty much set to go. So really what what I'm going to try and cover. I can't walk around because if I walk away from this mic, then I won't be able to be heard, so it's a bit unfortunate, but anyway, I'll just stand here. What I'm going to try and cover, as I was saying, the first half is very much just looking through the BGP basics. We might get a little bit into scaling BGP. The second section will finish off the scaling piece. A brief touch into using communities in BGP, which are generally another scaling technique in any case. And then we'll look at deploying BGP in a general service provider network. So the first bit, what is it? What is BGP all about? Well, it is if not the routing protocol that's used to exchange information between different networks. So different networks being different service providers, commercial networks, pretty much any obvious single network entity that you're aware of, small business, medium business, whatever, that is pretty much of interest for folks who want to try and use BGP. It's what's known as an exterior gateway protocol. It is the only exterior gateway protocol in use on the internet today. Described in RFC 4271, that is basically the BGP specification, the BGP standard. Some of you may be aware of the old one, the old specification document, RFC 1771. That was superseded, what, a couple of years ago now? So 4271 pretty much documents what the current practices is for a lot of the BGP implementations these days. 4276 gives an implementation report on BGP, so folks who've actually sat down and had to go and implement BGP on whatever platform have written about their experiences. So if you want to read about that, or if you're interested in writing your own code, have a look in there. 4277, a few service providers have actually described their own operational experiences from using BGP. So again, if you're interested in those documented experiences, have a look-see. The autonomous system is pretty much the cornerstone of BGP itself. So an autonomous system is generally used to uniquely identify networks which have a common routing policy. So basically, if you want to think of it as, well, you've got a collection of routers all connected together and you run them, you own them, you will use BGP to talk to other service providers to basically indicate the reachability you have across the network. So as I've said, they're a collection of networks with the same routing policy because you're going to present yourself with a unique view to the world. Single routing protocol, well, generally you won't have multiple routing protocols within one autonomous system. Some folks do, but generally you don't. Usually single ownership, trust, and administrative control. I say usually, it's not 100% the case because there are some situations where you get multiple entities who decide to use one autonomous system to represent themselves to the world. I won't really recommend it, but obviously if folks can exist in that environment, good for them. And they're identified by a unique number called the autonomous system number. Now, I know that some of you here come to my tutorials to see what I've changed. Well, here's something I have changed. Autonomous system number, it's a 32-bit integer. Okay? This is new stuff. It's a 32-bit integer. The two ranges, 0 to 65535, which was the original 16-bit range that we have been using for years and years and years and years. 65536 up to that very big number there is a 32-bit range. Well, actually the entire range is a 32-bit range, but RFC 4893 basically defines the extended autonomous system number range. The reason I have changed this slide is really from next year, the regional internet registries, as we'll mention coming, will be distributing 32-bit AS numbers by default as from 1st of January next year. So using these 1 to 64511 are for the public internet. We've got a private range, 64512 to 65534. 23456 is being used to represent the 32-bit range in the 16-bit world, in other words, on routers that don't know what the 32-bit ASNs are. 0 and 65535 are reserved, and then, well, the rest are basically for use in the public internet as well so far. 32-bit range representation is sitting in IETF last call. basically defining AS plain, which is the traditional format that we're using every day for the 16-bit integers, as the standard notation. So you kind of all need to be aware of this, especially if you're new to BGP and, well, you go asking Aaron or whoever for an AS number next year. They'll be giving you a big number, perhaps. They might give you a smaller number as well if you're actually aware of this and your router can't actually do it. You also need to go and ensure that your vendors will give you a router that will actually support the big number too. So that's still, let's say, is still work in progress. I haven't actually put in a URL here that lists who supports what yet, but I would say by the end of next year, pretty much every vendor should be supporting the extended 32-bit range. Okay, so the AS numbers supported by the distributed by the regional internet registries. Currently, we're up to 49,151 being handed out to the regional internet registries. So that's about 15,000 of the 16-bit range that are left. And we're using these at about, what, 5,000 or 6,000 a year, thereabouts. It seems to vary, but it's around about 5,000 or so a year. So in about 3 years' time, there really will be none left at all in the 16-bit range. Of these, around 29,500 are visible on the internet. Again, depends where you look, but in my view, about 29,500, which means there are around about 14,500 or so that you cannot see. Doesn't necessarily mean they're not being used, but it means that you cannot see them in the table today. The registries have also received 1,024 of the 32-bit ASNs each. Not very many of these are visible. Certainly in my view, I can only see about 12 of these. And a lot of them seem to be early adopters, although I noticed one ASN is now announcing about 500 prefixes. So maybe they're not an early adopter, but an early user. As in they're no longer experimenting by just simply announcing 1/24 and see what happens. If you're interested in all these ranges, the IANA document the actual assignments that have been made, both to the registries as well as some of the historical ones. So, getting into the BGP basics, BGP runs over TCP, port 179. If you're setting up filters on the edge of your network, especially those of you who seem to think that firewalls are great things to protect your network from other networks, remember to allow port 179 through your firewall filters. Over the years, I've spent a lot of time helping get BGP up and running for people who have loved to put firewalls in the place and forgotten to allow ports 179 through. BGP relies on incremental updates. So in other words, if anything changes within the network, the infrastructure, BGP will tell its neighboring devices, its peers, what this particular change has been. BGP table today is around about, what, 270,000 prefixes-ish, depending where you look. So trying to send that entire table every time BGP needs to make a change doesn't really work. Okay, as some of you probably know from using BGP, trying to load a full BGP table in takes a few minutes, many minutes, even quite a long time, depending on the devices used. Another thing I want to introduce here is this concept of internal and external BGP. Yes, BGP is one routing protocol, but external BGP is used for a very different purpose from what internal BGP is actually used for. And I'm going to cover the differences between the two in the next few slides. It's actually quite important, especially when you come to doing policies a little bit later on. What you use, what you see for internal BGP within your network is actually very different from what you should be using or distributing to other ISPs by external BGP. So we'll take a look at this. I've just got some terminology here. I mean, this is a little bit more. The demarcation zone is generally what's called the bit of network that sits between autonomous systems. So, for example, going between, say, AS100, AS101, the demarcation network is the link between A and C. Generally, a point-to-point link like this, it's jointly owned by both autonomous systems, or nobody owns it, or whatever. Or it could be something like this, where you've got a shared media, this could be Ethernet, where 3 autonomous systems will connect to each other. Again, nobody owns it, or it's owned by somebody else, or it's jointly owned. Okay, so that's a demarcation network. Generally, that's what folks around the industry are calling it. BGP will learn multiple paths via internal and external speakers. So we have internal BGP speakers, we've got external BGP speakers. It'll pick the best path. There's a defined set of rules which will pick the best path, and that best path is installed into the forwarding table. Best path is sent to external neighbors. Okay, it's not all paths, we just send the best path to external neighbors, and policies are applied by influencing the best path selection. So that's how we implement policies within BGP. So again, we'll see this later on. I'll cover what the best path selection process is, and then look at how we implement some policies by doing that. Now, I mentioned eBGP and iBGP before, that they are different. What iBGP is, well, the name suggests, is used inside your network. It runs inside the autonomous system. Okay, so you've got a collection of routers inside your network. Some of them will talk to external neighbors, but inside, they will all need to talk to each other so that the information you learn from your external neighbors will be distributed across your infrastructure. So as I say here, iBGP is used to carry some or all of the internet prefixes across the service provider backbone, and it's where you put your ISP customer prefixes. In the old days, many, many, many years ago, people didn't really bother much with iBGP. What they tend to do was dump the customer prefixes into OSPF or ISIS, and then somewhere on the edge of the network, they would either just redistribute them into BGP, or they would do some kind of static configuration so that these prefixes would be announced to the internet. That's very much ancient technology, I would put it. In the ISP I used to work for, when we started off with the iBGP pretty much like this from day one, and day one was 1992. So iBGP today traditionally is used to carry internet prefixes across your backbone as well as your customer prefixes. You've got customers connecting to your network, you drop their prefixes into iBGP. And eBGP is used to exchange prefixes with other autonomous systems. So in other words, when you're talking to another autonomous system, another network, another service provider, customer of yours, you would be using external BGP. And that's where you implement your routing policy. It's highly unusual to see any routing policy applied for internal BGP. Some ISPs do it, but it's quite unusual to see something like this. Policy is generally applied on external BGP sessions. So I've drawn a little picture of what the model is really like. So each of these bins is meant to represent a different autonomous system. So we run our interior routing protocol in here. Our interior routing protocol is just so our routers can see each other. That's all it's used for. So a well-designed network will have IGP, whether you use ISIS or OSPF, to ensure that your routers can see each other. We have iBGP, where your customer prefixes, your hosting LANs, and all this other kind of stuff, that will go into your iBGP. And then external BGP is used to basically distribute prefixes from your autonomous system to the neighboring autonomous system. So that's why I've drawn the model like this, where eBGP basically is a link between the two or adjacent networks. So look at eBGP. Here the speakers are in different autonomous systems. Should be no surprise that. I mean, external BGP, we're talking to somebody else in a different AS. Here the neighbors should be directly connected. Okay, they don't have to be, but that's very much more an unusual situation, corner case if you like. I generally like to see external BGP speakers physically connected to each other. As soon as you have any other infrastructure in between the two external speakers, you're creating potential areas of problems or difficulties within the network. So generally the nicest way of doing it, best way of doing it, is have direct physical connection as we have here between the two eBGP speakers. I've seen some horror cases. Some ISPs run an interior routing protocol between the eBGP speakers because, hey, well, I don't want to use connected. I know I've got some dumb device in the middle that doesn't know how to do BGP, but it can do OSPF or RIP just nicely, right? Interior routing protocol is just that. It runs inside the network. Never run it on the demarcation link. Some of the common newcomer errors that people make. So having physically direct connections between the two BGP speakers is generally the accepted way of doing things these days. Internal BGP is different. I won't go as far as saying it's a different routing protocol, but to all intents and purposes, it is actually very different in how it's implemented. Obviously, it's talking BGP to a router within the same autonomous system. So when you're configuring internal BGP, you'll be talking to something else in the same autonomous system. There's no requirement to be directly connected. Big change. Because you have an interior routing protocol ensuring that your routers can see each other. So all that your iBGP speakers need to see is the address of where the neighboring speaker is, and it will learn that via the IGP. Of course, OSPF and ISIs converge much more quickly than BGP will do. These days, a lot of ISPs are tuning the IGPs to converge in a few seconds. And so convergence for the IGP, so if any path within the backbone breaks, then your iBGP is unaffected because OSPF will, or ISIs will figure out which alternative path to take. You definitely don't want your iBGP infrastructure to fall to pieces during an infrastructure break. Also, this is a difficult one. I start off trying to show you what the basics of iBGP are. So if you look at the spec, iBGP speakers have to be fully meshed. Now, if we think about this particular one, well, what does a big network do? We've got 1,000 routers. Do we fully mesh iBGP for a 1,000 router network? No, we don't. And I'll come to this a little bit later on. But the actual basic BGP spec says iBGP speakers have to be fully meshed. They originate connected networks, so prefixes that are connected to the actual router itself will be dropped into iBGP. They will pass on prefixes learned from outside the autonomous system. So prefixes learned from an external BGP speaker, but they will not pass on prefixes learned from other internal BGP speakers. That's an important thing to remember. Again, newcomers to iBGP, and maybe some not so newcomers to iBGP as well, tend to forget this. So it's really important that every iBGP speaker in the network talks to every other one. It's fine for a network with 5, 10, 15 routers, and as I was saying before, once you get to 1,000, you have a wee bit of a scaling problem. So we'll look at this a little bit later on to see what the solution to that is. But the basic spec is saying iBGP has to be fully meshed. So it could look something like this. iBGP doesn't really care what the topology, the infrastructure looks like. Just every iBGP speaking router needs to speak to every other iBGP speaking router. The other thing that's quite important at this stage is this concept. We run iBGP between the loopback interfaces on the devices. I mean, if we ran the iBGP on the actual point-to-point link, I mean, that would work fine too. And I've seen networks that work like this. They work perfectly well, no issues, until a link goes down. See, if this link goes down, well, the iBGP running on the point-to-point link, well, this router here talks to this one here on the point-to-point link. The link goes down. What happens? Well, the iBGP session goes down. iBGP only announces prefixes that it hears from outside the network. So this router here, I should really put names onto them, but this router here, it learns external prefixes, passes them on to this router there. But because this link is down, this router doesn't hear about them at all. Right? This one here is not going to take those prefixes and pass them on there, right? Because the standard iBGP spec says we only pass on prefixes we learn from outside our network. Because this router down here assumes this one here assumes that this one here is going to get the prefixes directly. This router over here has no way of knowing that this link has gone down. Now, this is a classic disconnect symptom. You know, you can sit here in your NOC, and your customer phones in and says, oh, I can't see such and such a customer. All right, so you get the issue of the folks here can't see anybody there, and people here can't see anybody there. You sit in your NOC, you can see them, they can see them, and you can see both sides. So your customers phone and say, I can't see such and such, and so forth, and you say, no, well, I can see them fine, go away, stop annoying me. I've seen this happen a lot, okay? Go reboot your PC, go reboot your router, usual issues. But it's a classic IBGP breakage problem. You know, I cover this in the troubleshooting tutorial that I also do. It's a classic IBGP that gets many people, certainly who are more newcomers to this. If we run IBGP between the loopback interfaces, things are changed. Right? We run IBGP between the loopback, this sort of looped over arrow is meant to be the loopback. Run IBGP this way. This link breaks, what happens? Well, this router here says, can't get along this link anymore. How do I get to loopback over there? I can go around this way. OSPF converges, flips over 2-3 seconds, or whatever you've tuned it to be, and well, IBGP doesn't see any difference. Its neighbor is still the loopback, the IBGP session stays up, everything is happy. Okay, so generally if you want to ensure stability for your IBGP, run it between the loopback interfaces in the router like this. Some folks have maybe only got one point of presence and just one LAN and say, well, you know, can we not just run it between the Ethernets on the LAN? Well, sure you can. I mean, you don't have a redundancy situation like this. But what happens if you come along in the future and get some redundancy? Do you want to then go and reconfigure all your IBGP so that it sits on the loopbacks instead? So it kind of makes sense just to deploy IBGP running between the loopbacks from the start. All the networks I've been involved in helping build up, we just deploy IBGP between the loopbacks, then we never have to go and reconfigure the network in future. Okay? So that's pretty important. We don't want IBGP to depend on what the physical topology is actually doing. Now, the next piece, we want to have a look at the BGP attributes. And I've subtitled this information about BGP. It should probably be more like information about prefixes and so forth. I mean, when we drop a prefix into BGP, we don't just kind of just drop it in there and say, oh yeah, go have fun out on the internet type thing. There are quite a few other bits and pieces we want to put along with this prefix. And I suppose the best way of calling these bits and pieces are the BGP attributes. So we can store information about where the prefix has been, any priorities you want to put on the prefix and so forth. You can store this sort of information. These are the BGP attributes. So the first one I want to look at is the AS path. This one is pretty important. It's a sequence of ASs a route has actually traversed. So if we introduce a prefix, say here in AS100, 180.10/16, 100 will announce it to AS200, they announce it to 300, they send it to 500. We sit in a router in AS500, we look at 180.10/16, we can see a string of numbers in the AS path. And that's a list of autonomous systems that you have passed, or that prefix has passed through. So originated by AS100, 100 has sent it to 200, and we have heard it from 300. For those of you who travel far too much, like me, you know, when you check in at the airports, you get a baggage label printed out, and you get a list of, well, stops, basically, where your suitcase is going to be moved from one flight to another one. Similar sort of idea, but in reverse. So it's a list of destinations you've been to through the network. Okay, so that's the AS path. It's very, very useful for loop detection. Obviously, you know, if AS500 eventually gets back around to AS100, you don't want to end up with announcements spinning round and round until you run out of memory on the router. It's also very useful for applying policy. Because you can look at the AS path, you can apply policies. You can say, oh, I don't want any prefixes that have gone through AS200, for example. So you can do this kind of stuff, and we'll have a look at this a little bit later on as well. But that's typical reasons of why we find AS path very useful. I've mixed in 16-bit and 32-bit AS numbers for fun, just because this is all a coming situation for all of us. So I've got an AS 80,000 here and an AS 70,000 there. Pick them out of thin air, which is probably not a good idea, but anyway. So if we sit on a router, see AS 400, which is an old, living in the 16-bit world, and has no clue what these 32-bit AS numbers look like. Well, the AS path for 180.10/16 looks like 300. Remember I mentioned this 23456 earlier? 23456 is an old router will represent the new 32-bit AS numbers. So it can't tell whether this is 80,000 or 70,000 or whatever. It just sees them as, well, a 32-bit AS number, and I'll just put 2, 3, 4, 5, 6 in there to mark it. So that's what it actually looks like. Okay, so AS400 can see the prefixes coming from 32-bit AS numbers, but it can't tell which 32-bit AS number it is. Now, it's funny, until about probably 6 months ago, ISPs were like, oh yeah, fine, that's all nice and good. And it's probably about the last 4 or 5 months, folks have been coming to me and saying, oh, but how do I do policy on these 32-bit AS numbers and my router doesn't support them? And I'm like, I don't know. But can't you do something to get it to sort of find out what they are? Yes, you ask your vendor for images that have 32-bit AS number support. So one with 32-bit AS number support, you can actually see what the 32-bit AS numbers are, and so you stand a chance of doing the policy there. Okay, so that's what it'll look like. So, I mean, I've got a router that's sitting in this space, and that's what what the AS paths look like. So if you go home today or log into your router from here, you can probably do a show IP BGP or whatever you use, and you'll see the 2, 3, 4, 5, 6s appearing. I don't know, there are probably about a dozen of them. It depends where you look. I see about a dozen different ones appearing at the moment. If you're lucky and you've got one that supports all the new stuff as well, then you'll see what they actually are. Okay, the loop detection piece. So this is just coming back to what I mentioned before. If AS500 connects back to AS100, well, if we didn't have any of this loop detection stuff and none of the other safety checks in the BGP spec, then, well, 180.10.16 is sitting here in AS500. It's been learned from 100 all through this way. AS500 could just send that back to AS100. And with no checks or anything, it would just go round and round and round and round. Obviously, this doesn't happen because the software and the specification says that this can't happen. We'll just run out of memory otherwise. So AS500 probably would send 180.10.16 to AS100. 100 goes, huh, this is weird. This is a prefix that's got my AS in the AS path. So it sees the announcement coming in here on the border router in here, and it says, well, 180.10.16 AS path has got AS100 there. It will ignore it. Okay, so that's one thing to watch. So if you will never accept a prefix that has got your AS number in the AS path. Right? You will never accept a prefix from an external peer that has your AS number in the AS path. So that's an important thing to remember. I probably shouldn't mention it here, but sometimes you see this happening, and it's called AS path poisoning. And it's usually when an ISP, he'll insert another provider's AS into the AS path when he announces it to the world. And that's a very good way of ensuring that you don't get into that service provider's network at all. Because they're going to discard your prefix because they see their AS in the AS path that you've sent out. So again, you can have a look in the internet. I mean, somebody did a study about 2 years ago, and there were about a dozen of these. And it was hard to figure out if they were configuration errors or deliberate. Looking at 2 or 3 of them, I was pretty sure they were deliberate. Okay, it's what's called AS path poisoning. And now they're abusing this loop detection thing in BGP. Okay, so that's loop detection. Next bit. So this is the next attribute I want to have a look at. And this is quite a simple one. And it's called the next hop. And it's basically the IP address of the neighboring BGP router. Now, for external BGP, we're sitting on router B here. We learn a prefix from A and AS200. The next hop is the address of router A on the point-to-point link that talks to B. Simple as that. So when you learn this prefix 150.10/16 coming from AS200, your next hop address will be 150.10.11. Okay, so that's fairly straightforward. Here's the next gotcha. Next gotcha is, well, router C. What will the next hop address be actually there? Well, again, the standard is pretty much the next hop address is maintained in iBGP. Now, eBGP, the next hop address is changed. For iBGP, it is maintained by default. So what happens is router C will see 150.10.16 with the same next hop address. Okay, it sees it with the same next hop address. So router C has to know how to get to router A directly. Now again, this is a common error that a lot of newcomers to BGP make. Now I do loads and loads of these BGP workshops, which again just introduce folks to bringing up an IGP and iBGP in the network, and it's guaranteed that half the class will forget that router C needs to know how to get to 150.10.11, for example. Guaranteed half will actually forget to do it, even though I stand up here and say, you need to remember to do this. And the workshop note says, don't forget that. And it's still forgotten. It's really, really important. It means that this point-to-point link address has to be transported through AS300. And it means that point-to-point link address has to be transported by internal routing protocol, so OSPF or ISIs, if you're using that. Okay? So for a small network with only 2 or 3 external connections, this is fine. For a big provider, transit provider, and so forth, they end up carrying hundreds of these external point-to-point links through their backbone. They don't particularly like doing this very much at all. So a couple of slides' time, I'll explain why. Okay, but that's the next hop attribute. It's mandatory attribute non-transitive. So in other words, it stays just inside the autonomous system. For internal BGP, if you introduce a prefix into internal BGP, say 120.11/24, well, you're peering all your iBGP between the loopbacks anyway. So if you look at any other router, you'll see the next hop pointing to the loopback address. Right? So the next hop for 120.11/24 is the loopback's IP address, because we're running iBGP between the loopback interfaces. So this is actually really nice. It means that you detach your internal BGP completely from your physical infrastructure. All your internal next hops are loopback interfaces, which means that OSPF or ISIS takes care about how to get to that particular point of the network. So as I was saying before, if any part of the infrastructure breaks, well, you're only relying on loopbacks, and your IGP can rapidly reroute to get to the loopbacks much more easily than trying to handle all the changing a massive amount of next hops. If your next hop was a physical address and you're to charge through your entire routing table changing next hop addresses, that takes a finite amount of time on the router. And a finite amount of time is not, well, it's not something that you won't notice. You will notice it. Whereas if you do it like this, if you run iBGP between the loopbacks and any infrastructure breaks, there's no next hop change, stability is maintained. I mean, I know some networks where the infrastructure they've got is really crummy, but they can run a very, very stable iBGP simply because they've followed this particular advice. Okay, third-party next hop. Kind of got to watch this one. This is put in for efficiency. I was there for efficiency. It can be a bit of a downside, especially at internet exchange points as well, but at internet exchange points. But this is how it works. The idea is, you know, if router A and B are peering with each other, B is sending this 120.681/24 prefix to A is peering with C and sending that prefix on to C. Well, all these routers are sitting on the same LAN. So the next hop address that C will use is still 151.1.3. It's not changed. Right, so B will send, well, my address is 151.1.3 to A. A goes, that's the same network, so that's fine. 151.1.3 is what it is. A sends a prefix on to C with the same address, 151.1.3. C says, yep, that's the same subnet, so it will use it. So traffic from C to B will actually just go straight. It won't boomerang through router A or bounce through router A. Okay, so that's a third-party next hop. It's done for efficiency. At exchange points, it can get a little bit strange because, well, AS200 may not want to peer with AS201. Okay, yet you could still end up having traffic going that way simply through the third-party next hop piece. So you kind of have to watch that. So you don't have to do any special configuration to make sure that third-party next hop works. It's just there. It just happens. Now, the best practice for next hop, or best hop, next practice? No. Next hop, best practice. Right, the BGP default is for the external next hop to be propagated unchanged to the iBGP peers, right? That's our default. Which means that your IGP is going to have to carry all these external next hops. Now, if you're like me, you probably have loads and loads of eBGP peers, you have your transit providers, you'll be at internet exchange points, you'll have all your customers connecting to, you'll drop their prefixes into iBGP as well. That means you're going to have to carry all your external next hops. So your IGP could go from, say, 200 prefixes to represent your backbone to maybe 10,000 prefixes just to carry all your external links. Not nice. You really don't want to do that. That will substantially slow down your convergence of your IGP. Right? And if you forget it, it means the external network becomes invisible as well. So if you just miss it out by mistake, it means your external network becomes invisible. And I've seen this happen quite a lot too. And so it puts quite a lot of load on your IGP. So the best practice is to change the external next hop to be that of the local router. Now again, what the command to do it depends on implementation. I mean, the Cisco iOS one is next hop self on the BGP peers. Okay? So you look up your own implementation to see what it is. And what next hop self does, it changes the learned external next hop from the point-to-point link to be that of the local router. And because the local router is using loopbacks for iBGP peering, the local next hop that's going to be used will be the local loopback address. So you've now divorced your external connectivity from your internal infrastructure as well. And that's very important too. So we've now got all the right ways of trying to set up iBGP in an ISP network. So we peer iBGP between loopback interfaces. We set next hop self on all our internal BGP peerings. Because remember, it's the prefixes learned from outside. When we pass the prefix on to another internal speaker, we want to change the next hop to be that of ourselves. Okay? So that's pretty much the ISP best practice these days. I mean, certainly any of the well-run networks that I've looked at these days do this. Okay? Summary of all that, IGP should carry the route to the next hops. We use recursive route lookups, again with the loopback and so forth. The IGP looks up the loopback, how to get there. We unlink BGP from the physical topology. We change external next hops to be that of the local router, and we let our IGP make the intelligent forwarding decision. Okay? BGP was never ever designed to be a fast-moving, agile routing protocol. You can think about it as the slow, lumbering truck carrying loads and loads of, well, load. I'll say BGP table today, 270,000 prefixes, big. Your IGP, people invested quite a lot of time to get OSPF and ISIs converging really, really quickly. You can stick with all your manufacturer defaults. A lot of people now are tuning these numbers way, way down to get a few seconds, even a second or so convergence. So why wreck your IGP by putting a huge number of prefixes in there? Try and keep the IGP prefixes as small as possible. What do we say? Well, if you can count the number of routers in the backbone and the point-to-point links within the backbone, then you've probably got about your IGP size. So you can see how some of the really big service provider networks run efficiently today. Next one, Origin. Origin is, well, in my humble opinion, it's historical attribute. It's still there within BGP. I don't really think anybody uses it that much anymore. It doesn't convey the origin of the prefix as in like which country it came from or which ISP it came from. It says which routing protocol it came from. Did it come from BGP? Did it come from ye old EGP routing protocol from 1980 something or other? Or did it come from another routing protocol process altogether? Was it redistributed from, say, statics or OSPF or whatever? It's used to influence the best path selection. So this was part of the transition from the old EGP protocol into BGP. We're trying to get the internet off EGP to actually use BGP. I think this was like even before my time in ISP land that this even happened. So this is still hanging around here. The three values, and again, they're defined in the spec as being IGP, EGP, and complete. And again, quite honestly, newcomers to BGP find this confusing because I've just been talking about IGP as an OSPF and ISIS, and then we see IGP here, and that's not OSPF or ISIS. This IGP here actually means it's come from BGP itself. Okay? This EGP here does not refer to BGP as being an exterior gateway protocol. This one actually refers to the old EGP protocol. Certainly, if you've got any old Cisco routers from 12.2 and before, you can still do router EGP in them. Okay? It was that old EGP routing protocol. Incomplete, well, if you're redistributing, some people will redistribute from static into BGP. then you'll see the origin incomplete. Okay, so those are the three origin values. Aggregator, another attribute, conveys the IP address of the router or BGP speaker which generated the aggregate. So if you use, say, a command to generate the aggregate on the router, again, the one in Cisco is aggregate address, that will set the aggregator attribute. Pretty useful for troubleshooting if you're trying to work out where the aggregate came from. It's pretty useless for anything else. Okay, it's not used in the path selection or anything else that BGP does. It's purely there to provide information as to who or what in the network generated an aggregate. Next attribute, local preference. So we've got this situation. We've got AS100 originating 160.10/16. It lands up in AS400 going via AS200 and AS300. And we're sitting on router C, and we say to router C, right, send traffic to 160.10/16. Well, routers are computers. They're dumb. They do what they're told. Now, we as humans can stand and look at this and go, ooh, well, maybe we can go through AS200 today, or maybe we'll go through AS300 tomorrow. So we can do that. Routers don't have this kind of random kind of logic-making process within them. So they need to be told what to do. And this is where local preference comes in. Right? So what we can do is we can say, well, if we put a local preference of 800 on the announcement coming in this way, and local preference of 500 on the announcement coming in this way, we look at router C, we see two paths. We would see two paths anyway, but we see two paths now with different local preferences set. So the first path, local preference 500, second path, local preference 800. So this way we can tell router C which outbound path to take. Okay? Highest local preference wins. So traffic from C to AS100 will go out this way. Local preference is useful for you to steer traffic out of your network. It is the ultimate attribute. It overrides everything else that anybody can do on the internet. Okay, so if you see traffic going weird ways out of your network, you can override it. If you don't like the path chosen, you can force traffic out a particular link using local preference. If you can figure out how to set a local preference on your network, you're well on the way to be able to set up multi-homing, load balancing for your network itself. Right? So remember, no matter what anybody else does, you can override that with local preference for that particular prefix. Okay, so that's the local preference attribute. Summarizing, it's non-transitive attribute, so it's not passed from AS to AS. It's only visible inside your own autonomous system. It's optional. You don't have to set it. If it's not set, the default local preference in iOS is 100. It may be different on other implementations. It's used to influence path selection, determines best path for outbound traffic. So inbound routing announcements, it will influence outbound traffic flow. Highest local preference wins. Next one, MED. Well, for us old folks, we all call this metric, because that's what it was in BGP version 3. And then when BGP version 4 came along, the name was changed to MED, multi-exit discriminator. Pretty much does the same thing, but it works this way around. We're sitting here in AS201, 128.68.1/24, when it makes these announcements to AS200. We want to determine how traffic comes into our network from AS200. And so this is where we set the MED, or we set the metric. Okay, so if we set a metric, say 1,000 on this link, 2,000 on that link, the announcement ends up in AS200. The routers here will see two paths, one with metric 2,000, the other one with metric 1,000. Path with the lowest metric wins. So traffic will go from AS200 to 201 on the D2B link. So metrics are useful when you have a situation like this. You've got more than one link to a neighboring autonomous system. If you're connecting to different autonomous systems, the metric will be of no use whatsoever, right? Because metrics are not passed from ASs to ASs. Yes, you send a metric to your neighbor, they will not take that value and send it on any further. Okay, so MED is very, very useful if you want to tell your neighbor which path inbound traffic should take. So it's the opposite of local preference. Local preference steers outbound traffic, MED steers inbound traffic when you've got multiple links to the neighboring autonomous system. If you've got multiple links to different autonomous systems, you can't use MED for outbound traffic. Okay? Sorry, inbound traffic, outbound announcements. So summarizing this, inter AS, it's a non-transitive attribute, it's optional. It's used to convey the relative preference of entry points to the network. Comparable if paths are from the same AS. Your vendor may have put in a knob for you that you compare paths from different autonomous systems. I certainly think at least Cisco and Juniper have that. Path with the lowest MED wins. Absence of an MED attribute implies MED value of 0. Well, that was relatively new. That's RFC 4271. Before then, well, different vendors had different ideas of what absence of MED should mean. Well, if you think about it, if MED is not set, how do you compare a number with nothing, with a blank? You can't set a variable to blank, right? There's no way of doing it in programming. So you had to pick some kind of default. As a local preference default picked was 100. MED, well, Cisco picked 0 as the default. Other folks picked things like 2 to 32 minus 1 or 2 to 32 minus 2, having the view that, well, if the folks can't be bothered to set an MED here, then maybe it's not important. Whereas the Cisco view was, well, if we set an MED here, don't set an MED here, then it must be really important. And so you suddenly had interesting situations, this metric confusion, peering between ASs that use different BGP implementations. You ended up at one ISP would send no MED on one link and say 100 MED on the other link, assuming that the first link would have all the traffic and the second link would have none. Of course, the other AS was using a different vendor. They would see no MED in one link, set that to 232 minus 1, and see 100 on another link, say, okay, obviously the first one is really unimportant, let's send all the traffic on the second link. So you have the situation where MED was not doing what folks actually expected. So what you found was that a lot of ISPs just didn't bother using MEDs anymore. I mean, they would just basically override MEDs with local pref or something like this, so that they just were not supported in the network at all. So you find, looking around the internet today, that the support of MED is fairly variable, simply because we had this early confusion. I mean, RFC fixed it. 4271 did fix it, but that only came out 2 years ago, and we already have people using MEDs for at least 10, 12 years before that. But kind of to the rescue of MED came this thing called the community. And rather than using MEDs for signaling policy to a neighboring AS, ISPs started using communities. Communities appeared round about again 95, 96. Described in RFC 1997, it's a transitive attribute and it's optional. And it was a 32-bit integer. That was the original specification, but ISPs were like, okay, this is going to be a bit interesting to handle. In fact, some of the first implementations, well, the first ones I saw, Internet MCI, basically split the community into 2 pieces. So the first 16 bits they used to represent local autonomous system, and the second 16 bits they used to signal policy. So what would happen is the customers would send communities based on ASs and so forth, and they would define their AS colon a list of different communities to do different policies with customer prefixes. So that was documented in RFC 1998 just as an informational RFC. But the whole format kind of stuck. That's pretty much what we're using today. So the first 65,000, last 65,000 are reserved. The general convention for communities that you see people using these days is you see they put their local AS number in here or a private AS number in here, colon separator, and then it gives them up to 65,000 possible policy options. So much later on in the second half of the tutorial, I'll show you some ISP examples of typical communities that they use following this particular format. Now, the point of the community is to group destinations together. See, in the old days, before communities were around, I mean, certainly what we had to do was we had to implement multiple autonomous systems to get different policies. You know, if customers wanted different connectivity, we had to do a lot of jumping around with different autonomous systems, which just got messy. What we can do when communities came along was, if customers bought different services, we just tagged them with different communities. And then at the edge of the network, we could basically announce their prefixes depending on these different tags. So it was a very, very useful technique for actually implementing policies within SP networks. It certainly made things a lot easier. I mean, here's one kind of simple example of how it made it easier for us way back then. You say you've got ISP here, AS300, they connect a customer, AS100, so they set up a filter here which says, okay, allow 160.10/16 in. If we want to announce the prefix to AS400, we've then got to touch our filter on router E to let 160.10/16 out. And you say, yeah, well, so what? That's fine. Well, if we think back all those years ago, well, what did we have to do that? Set up a filter here. Okay, that's a new customer we're connecting, so that's fine. You know, it's a fresh session. But this one could be an established peering to our transit provider, for example. So we have to go here, update the filter. Well, back in those days, with no such thing as route refresh or anything like that to just gracefully update the BGP session. No, we had to shut the thing down, bring it back up again. And we tried to provide some quality of service to our customers, so we had to do this during our maintenance, which was 4 a.m. to 7 a.m. on Tuesdays and Thursdays. So a customer connects on Thursday lunchtime. He doesn't get internet access until 4 a.m. following Tuesday morning. I mean, that's great, sort of, yeah, we'll connect you and you get immediate connectivity. Yeah, we'll connect you, but we'll give you connectivity next week. Not many people were happy with that type of service. Okay? I mean, that's all we could really do because we didn't want to shut down our main transit link in the middle of the day when we connected a customer. Connect another customer. Okay, 170.10/16 in. We have to update our outbound filters there as well. Okay, to let them out. So again, same issues. It could only be done at particular times of the week. Okay, we just add another ISP peer. We don't have to change anything there. Yes, we update filters and so forth, but it doesn't impact the main piece. Now, if we use communities to do this, it becomes a bit easier. Prefix comes in here. We tag them with community 300:1. 300 is our AS number. :1 is, well, transit customers. So our filter on this border router here says, let anybody who belongs to community 300:1 out to AS400. We set up a one-time filter, and that's it, done. Finished. Connect our next customer. Okay, AS200, he's sending 170.10/16. We tag him with 300:1 as well. Guess what? This filter here is already set to allow 300:1 out. So no update is needed. Customer gets immediate access to the internet when he's connected. So we did this massive, massive upgrade in our policy. I think it was mid-1996 when this, was it 96, 95, whenever it first appeared in Cisco iOS. And we did this massive upgrade of our policy for all our transit customers. And we threw away our massive external filters that we had, and with a very, very simple one-line community filter that said, well, this community gets out to our transit providers. It greatly simplified how we did stuff. So communities are very, very easy for handling policy. And if you're not using them at the moment, I really strongly recommend that you go and have a look and see how it can help simplify things. Forgot this one. So yes, you're connecting somebody else, you don't want to be part of this piece, just put them in a different community, filters don't let them out, and it's all fine. What I was going to say, the four well-known communities, there's the no export, no advertise, there's the confederation one, which I'm not going to talk about, and then there's the no peer community down here as well. So no export is used a lot. No advertise I don't see used very much, and no peer, well, I've only heard of one ISP who actually claims that they use it, which is a bit of a shame. So, but I've got two examples of how they work. Here's the no export community. In this situation, if you're, say, have multiple connections to, say, a transit provider, something like this, you've got 3 links to your transit provider. The traditional way of trying to do load balancing on this is you take your address space, you announce your address space on the 3 links, but you also take your address space and divide it into 3 pieces. Okay? And you announce each piece on a different link. So first piece on link 1, second piece on link 2, third piece on link 3. And so what happens is all the traffic for the first piece comes in this way, all the traffic for the second piece comes in that way, all the traffic for the third piece comes in that way. And that gives you your load balancing, sort of. At least it's the first cut. But the whole world doesn't need to see these pieces. because your transit provider is just sending your entire aggregate out to the internet. You don't need to send the sub-prefixes out as well. There's no extra information to be gained by doing this. So what you do is you tag the pieces that you're sending on these links with the no export community. Router J here sees these prefixes tagged with no export and discards them. Okay, it will not announce anything with no export. So a lot of ISPs are actually using no export for this type of, if they're doing traffic engineering, load balancing between themselves and their peers over multiple connections like this. The no export is used quite a bit. Okay, so that's fairly commonly used. The next one is no peer. I think no peer community is a wonderful idea, but I don't know, where did I do this presentation? I did this presentation a while ago. I think it was a RIPE meeting or somewhere or other like this, and it was basically one ISP in Europe jumped to the microphone and said, I support them. It's like, well, that's very nice, but if nobody else in the room even actually knows what it is, it's a great shame. What the no peer community does is signal to your upstream whether this prefix should be sent to a peer or not. So here's one example. It's a bit of a messy picture, but the router A sitting this provider, he's got 3 upstreams. Again, he wants to do traffic engineering. Right? So he sends his aggregate out each of the 3 links. And as before, we want to send the 3 pieces. We split the aggregate into 3 pieces. So we send the first piece this way, the second piece that way, the third piece that way. Now in traditional multi-homing, the global ISP, the global routing table, will see the aggregate as well as the 3 sub-prefixes. Right? The 3 sub-prefixes give not much extra information over what the aggregate gives. It just says, well, traffic going to the first sub-prefix should go in through this way. Okay? And so what really we're trying to achieve with the no-peer community is, well, if we send a sub-prefix up with the no-peer community, router E here will see this prefix, it's tagged with no peer, which says, don't send this to a peer of mine. So it'll only send it to upstreams. It won't send it to peers. So you figure out who's a peer of yours or who's a transit provider of yours. You send it to your transit provider. You don't send it to your peer. Okay, and certainly the ISP who's implemented it this is what they've done. Okay, there's nothing in your router that you need to do. You just need to figure out what's a peer of yours and what is not a peer of yours. As I say, most times I give this presentation. If you think there should be something configured in the router, please let me know, and I'll try and spend the next year or 2 getting it done. But generally, what the idea is to reduce the amount of deaggregated nonsense or crud that we basically see in the full routing table at the moment. Okay, but if more ISPs would use it, then we'd hopefully see less sub-prefixes floating around in there. Okay, implementation details. Community is an optional attribute. I mean, you don't have to set it for every single prefix. And certainly if you're using more than one implementation within your network, you probably should try and figure out what the defaults are. Because some implementations don't send communities, some do send communities to IBGP peers, others don't. Some implementations will send communities to eBGP peers, and others won't. You do need to check what your vendor defaults are. If you're careless about it, you can end up with a bit of a mess. For example, don't just assume that if you tag a prefix with no export, that your neighbor will actually do something with it. I know many cases of that where an ISP, he's been to the tutorial, been whatever, and he's doing all the right thing, and he sends communities to his upstream, and his upstream ignores them. Okay? If your upstream supports communities, it's fine. If you're not sure, ask them. I mean, if they're good, they probably should support them to some extent. Don't just assume that they will handle, for example, no export. Okay? So again, watch what communities you send. I mean, I'm not sure there's really a great deal of need to send your communities to the whole wide world. They're useful between you and your neighboring providers and maybe one step further than that. But beyond that, I probably don't think there's a great need for that. I mean, why would anybody say, well, I don't know, pick a furthest point from the world from here? Why would they care what your community actually is? Okay, path selection. Where are we with time? Plenty of time. Right, this is the path selection algorithm. I've put the one on here for Cisco iOS. It's not wildly different from anybody else's. I mean, the path selection process is defined in the RFC. I've just thrown in one or two little extra bits and pieces as you see them in iOS. Other implementations have thrown in their one or two bits and pieces as well. They generally behave all the same way and do all the same thing. Again, a word of warning, if you've got a multi-vendor network, try and make sure the path selection process works the same way. You use all the same knobs, bells, and whistles, and so forth. Otherwise, you could end up with some really weird results. First one, do not consider path if there's no route to the next hop. I would like to think that's a statement of the obvious, but you'd be amazed the amount of situations I come across where people are going, well, why is it not picking this path? It's got a next hop address. Who cares if the next hop address? If the router doesn't know how to get to the address, it's not going to use the next hop. So that's the one. Remember us saying the next hop is, you do the next hop self thing for iBGP, because if the next hop is outside your network and you learn a prefix with a next hop that's not reachable, the path is not going to be used because of step one. Okay, that's why it's really important you either transport your external next hops through your IGP, or you do next hop self to set it to your edge router. The second one is weird for Cisco, and it more or less goes away now unless you use really old software. Third one, highest weight. Now, weight is not a BGP attribute, but again, pretty much every BGP implementation I've seen uses the weight. And the weight is a local preference that's used on the router, local router itself. Weight is not passed from router to router. It's only on the router. So it's a bit like a local preference. So again, for comparing two paths, highest local preference wins. Okay? So you see pretty much local preferences first. That's why I said earlier, local preference will override anything that anybody else does. Right? So local preference basically comes first. If the local preference values are the same, we then prefer the locally originated route. Okay? Kind of makes sense. You know, if it's been originated locally, why not you going to prefer something that's come from somewhere else? Otherwise, we pick the shortest AS path. This actually wasn't in the original BGP spec, but pretty much everybody implemented that. Shortest AS path. Why jump through 10 hops when we can just go through 2? That's basically what that's saying. Okay, so we pick the shortest AS path. If the AS path lengths are the same, well, here's the origin. We prefer BGP before the old exterior gateway protocol, before something that's been redistributed. Okay, generally, origin code doesn't come into play anymore these days because most folks are using BGP now. After that, we compare MED. And by default, we compare MED if paths are from the same AS. Okay, if paths are from the same AS, we compare MED. If paths are not from the same AS, we move on. But many, many years ago, big ISPs who have multiple links to each other said, well, but we always want to be able to compare MEDs, no matter which AS they've taken. So there's actually a knob, certainly in iOS, and will be in other implementations too, which says compare the MED regardless of the neighboring AS. Okay, so some people want to be able to do that. So if you've got this knob enabled, then it will compare MEDs even if the paths are from different ASs. This one's important as well. Long time ago, this BGP spec never said anything about what the order of paths should be. But then long time ago, when the internet all started, ISPs maybe had 1 or 2 links to each other. They certainly didn't have 20, 30, 40 links to each other, as you see more often these days. And so what happened long time ago, well, you had 1 or 2 links, all was fine. Once you got loads of links, then, well, how should the paths be ordered? If you've got 20 links to your neighboring ISP, what order should the paths be in? Well, the order of the paths usually determines the result of the best path selection. So if you do maintenance on your best path, it goes to the bottom of the list. And then you do your selection again, you get a different result. And the issue was, without this deterministic MED, the issue was that you get a different best path depending on the order of the prefixes were learned by the router. Now, this didn't matter 15 years ago, but it does matter quite a lot today. So again, this is actually a good practice recommendation. Some implementations have it by default, but iOS still does not have it by default. is this BGP deterministic MED. The paths are ordered according to AS number, ascending AS number. Okay? So no matter what maintenance you do on any of the links, they'll be reinstated in the same order before the MED comparison is done. Again, I'll refer you to the troubleshooting tutorial. I've got one example of where deterministic MED is not used, and you can see the apparently random best path selection results happening. No, it is not a bug, it's just simply how the implementation was done of old. Anyway, part 3, if the MEDs are all the same, we prefer external path over internal path. Well, if the destination is outside our network, we don't want to carry the traffic anymore over our infrastructure because, well, this will be happening on an edge router, border router. If I know how to get to it out of my network, I'm not going to cross my backbone. You've heard of hot potato routing? That's what it is. It means get it out of my network as quickly as I can. And so eBGP path is preferred over any internal path. If the destination is not in my network, I'm not going to carry it any further across my network. And this one here, path with the lowest IGP metric to the next hop, basically says pick the nearest way or pick the fastest way to get to the exit. It could be biggest bandwidth, fewest number of hops, whatever, however you tune your IGP. Again, part of the hot potato routing. Get it out of my network as quickly as I can. Whoops. So if all these are still the same, we then pick a lowest router ID. We're now starting to get into a little bit scary country. We really don't want to have things dependent on router IDs and so forth. They change. Okay, you might redesign your network and the router IDs all get changed. And then your multi-homing, your load balancing that you've spent hours and weeks and days and months getting right, all changes. Okay, so once you're into here for the path selection process, it's starting to not get such good news. Cluster list I'll come to with the route reflector a bit later on. Finally, lowest neighbor IP address, definitely very scary. Okay, that's the IP address of the neighboring router. And that probably will change. Any growing network, your neighboring address will change. So having a path selection depending on neighbor address is probably not so good. And that's pretty much it. And as I was saying at the start, multi-vendor environments, please make sure that the path selection process is at least synchronized. So flick any switches, knobs, whatever you want to call them, on your different implementations to get them to do the same thing. Okay? Otherwise, you can end up with some really weird things going on within your network. Also, watch out for the MED confusion thing as well. You know, if your implementation has a default value of MED at 232-1 still, I mean, it shouldn't, but I mean, if it has, then you probably want to try and hardwire MED values or just ignore them altogether. And also watch out for this deterministic MED piece also. That should be default, certainly in a Cisco iOS configuration, that should be a default. At least it should be in any of your templates. Okay, policies. So applying policy with BGP. Well, network operators will rarely plug in the routers and off they go. I know a lot of people want to be able to do that, but for a service provider backbone, you probably don't really want that to be able to happen. You want to be able to set up your network and tune it appropriately for infrastructure. You've got external relationships. You want to control who you're going to peer with. You don't just want to peer with any old person that comes along, or well, maybe you do, but you need to be able to make that decision. You want to control who you give transit to. The days of giving free transit to the whole internet are probably gone. It still happens in V6 land, but generally in V4 land it doesn't really happen unless you make a mistake. And you also want to control who you get transit from. You do not want to get transit from your customer. Customers may want to give you transit. You probably don't want to do this, as their links are probably not as big as yours. So you need to be able to handle policy. It still pains me today to see BGP peerings without inbound and outbound policies. I mean, I suppose it's a personal view. I still would much prefer to see a router configuration, BGP not actually work until you've got inbound and outbound policies configured. But certainly in iOS, you can just do router BGP, neighbor, blah, and you're done, up and running. You accept everything and send everything, which is probably not wildly useful or helpful for operators these days. So managing external relationships is pretty important. You've got traffic flow control as well. You want to try and use the scarce infrastructure you've got as best as you can. So link, load balancing, and so forth. You want to try and avoid congestion. And this is what we call traffic engineering. Okay, so you really need to be able to try and sit down and figure out how to do traffic engineering. All the BGP attributes that I've described will let you do this traffic engineering. I'm not going to spend ages on how to do it. That's the multi-homing tutorial. Loads of examples in there. But the basics of the policies are that you can use things like local preference. Remember, local preference lets you determine outbound traffic flows for your network. We've got MED, which will let you determine inbound traffic flow on if you've got multiple links to a peer. AS path is really useful. I mean, you can determine if you want to prefer traffic through particular ASs or not. And the community is hugely useful, as I'll show you a bit later on. I've got some examples, as I said. Okay. There's also advertising and filtering prefixes. Again, what you announce, what you accept can all be very useful for applying policies. You can also filter prefixes according to the autonomous system number or according to the AS path, or both. All these, if you learn how to manipulate these, are very useful for applying policies. And the final one is according to community membership. But again, ISPs use communities. These communities will let you either control how your traffic flows or may tell you how to send traffic according to what a customer or a peer wants to do. So most implementations have tools, and I'm not going to I'm not going to spend any time giving any tutorial on how to use these tools. I'm sure your vendors will be delighted to punch you at documentation to do it. But generally, you've got tools that will let you manipulate prefixes, do the AS path stuff, the community stuff, and so forth. They also have a policy language. Again, different vendors have different policy languages that will do various matching of conditions, setting particular things, and so forth, to manipulate BGP routes that you're going to send or accept from your neighbors. Next, BGP capabilities. So is BGP extensible? The answer is generally yes, and it's done really through something called BGP capability negotiation. This is documented in RFC 2842. Generally, when you bring up any BGP session, what a BGP speak will do, it will say, hey, do you support capabilities as such? It's generally gone away from the issue of the old days where if you tried to do capability negotiation, the router would go, ooh, he's doing weird stuff to me, shut down. Okay. Certainly in like the late 90s, early 2000s, there were still some implementations out there that did that. But generally these days, if a router doesn't know what capability negotiation is about, it will just say, yeah, that's okay, I can't do this. Okay, and things carry on as normal. We don't have any of these go away. You're bad. So the different capability codes have been defined. I've listed the known ones here. So if your router supports multi-protocol BGP, for example, it's code 1. So that's the multi-protocol BGP. So for example, if you're doing MPLS, or you're doing V4 multicast, or you're doing V6, you need to support the multi-protocol extensions. Route refresh, I'm going to cover next. Outbound route filtering, that became an RFC about 2 days ago, I think. So I haven't really looked at exactly the implementation status of any of that one. Multiple routes to destination, I have no idea who's implemented any of that. Graceful restart is used more and more now. The 4x AS numbers I mentioned right at the start, so that's RFC 4893. And there are various other bits and pieces that are still lingering internet draft status. But generally, the IANA has listed the capability codes here that are available in BGP. So the multi-protocol extensions, that's a whole different world. I mean, BGP for a long time only ever supported IPv4 unicast. And it was a bit of a kind of hodgepodge in the, I suppose, mid-90s with people starting to put multicast into BGP, so carrying multicast prefixes around by BGP. And then, of course, the V6 folks going, ooh, this RIP V6 thing doesn't scale much anymore. Let's try and use BGP to carry V6 prefixes. So it got a bit mucky, messy, and so multi-protocol BGP was basically standardized as to specify how the different address families could get carried around by BGP. It's another tutorial. I mean, it's going through the whole multi-protocol piece. The MPLS tutorials have been here and gone. I'm going to do a V6 routing tutorial tomorrow at some stage, and that will show you the V6 piece of BGP also. This route refresh, I'm going to cover that in a bit. 32-bit AS numbers have just arrived. Well, they've been arrived now for 2 years, but it's still recent compared with some of the other ones. Okay, so I've got 10 minutes, so let's start making a look at the scaling BGP piece. How does a service provider scale the iBGP mesh? How do we implement new policy without causing flaps and churning and keep the network stable, scalable, and simple? So I mentioned one of the issues at the start when I was talking about the communities piece. When I said, oh, well, you know, in the days before the communities, well, we had to do prefix filters on all our peering routers. And to change any policy, we had to shut the router, well, the BGP session down and bring it back up again. Because BGP sends incremental updates. It only sends changes. Right? It only sends changes. So if you want to apply new filters to any announcements, you've basically got to send the entire update all over again. So that's route refresh, which I'm going to cover next. And I also mentioned, well, iBGP has to be fully meshed. That's what the spec says, and it's fine for 15, 20 routers. What do you do when you have 1,000? A full mesh iBGP is very scary at 1,000. So that's where route reflectors comes in. I've written confederations there in very light gray. The slides will be in the handout, but I'm not going to go through them here. Nobody's deploying confederations new these days. Pretty much anybody I know who's deploying BGP is using route reflectors because they're much, much easier to deploy, run, and all the rest. Saying that, there are quite a large number of ISPs who are actually using confederations quite happily today. Nothing wrong with them. It's just that the new providers, new networks are deploying using route reflectors. So I'll spend time going through that instead. So let's look at route refresh. Route refresh, basically, a peer reset is required after every policy change because, as I said, BGP only sends incremental updates. So if you want to apply a policy to an update that's already gone out, well, you can't exactly go to your neighboring router and say, oh, remember that update I sent 3 days ago? Can you take it away now? Well, you can't do it directly like that. That's where this route refresh comes in. Okay. What you had to do before route refresh was basically shut down the BGP session and then bring it back up again. Now, in 1993, this probably didn't matter because only a few of us were playing on the internet because the commercial networks were still using X25 or Frame Relay or whatever they were happy with using. And it was only us weird folk that were using IP. So if the network broke for 2 minutes or 3 minutes, yeah, it's just the internet, it was slow. These days, people are expecting commercial grade services. Everything should be working all of the time. So you can't just go hard reset on a BGP session just to get policy updates. So what route refresh does, basically it keeps the BGP session active and it only impacts the prefixes that are affected by the policy change. So that's what this route refresh is about. Whoops. So most implementations will now support it. I mean, there was a day, again, probably about 7, 8 years ago where not everybody supported it, so we had interesting hacks to work around it. But pretty much these days, it's there, happening on all your implementations. They just do it, and you don't even are aware of it. Doesn't need any extra memory. What happens is basically the router, when you do a route refresh, it sends a notification to the peer saying, which basically says, oh, I've changed my policy. Please send me all your announcements again. Right, so it just sends a notification to the remote peer, send all your announcements. And so if you get a full BGP table from your neighbor, you no longer need to shut down the session, bring it up again to get the full table. You send a notification to your peer, and they send their entire BGP table to you again. And because you've revised your inbound policy, the prefixes affected by the inbound policy are what's affected. So if your prefixes which are not affected by the policy will not have any traffic or anything else affected either. So it's a non-disruptive change. RFC 2918 describes this. So I say use route refresh capability if it's supported. It should be there in most of your configurations. The implementations that don't support route refresh, I'm actually not aware of any anymore these days. There may still be some really old ones lurking out there. And if you do find a peer that's still got some really, really old BGP out there, well, probably try and encourage them to upgrade first to something slightly modern. If not, you usually have some kind of soft reconfiguration feature that will let you work around. I mean, there's one, and certainly most of the implementations, again, that I know of, where you get a soft reconfiguration feature that lets you work around the lack of this route refresh. And as I say there, only use a hard reset as an ultimate last resort. Consider the impact the same as a router reboot. Certainly if you're carrying the full BGP table these days, it takes about the same amount of time. I mean, if your customers don't mind 5-minute outages every now and then, yeah, go for it. But I generally try and discourage the hard reset of BGP. Okay, next piece. I think I'll do the route reflector bit and then we'll have our break. So let's have a look at the route reflectors. So as I was saying at the start, having a few peers is very, very easy to do a full IBGP mesh. But the problem is, the more routers you add, it does actually go up by n squared. So 13 routers, 78 IBGP sessions. 1,000 routers, 500,000 IBGP sessions. There are quite a few networks out there that have got more than 1,000 routers. Can you imagine doing a full IBGP mesh in any of those? Probably not. So this actually came to the fore probably about 96 was this, early 96. I should check my dates sometime. I mean, all the accidents that caused these changes are burnt into my mind. I just don't remember the years anymore. But this was pretty major. It affected us in a pretty major way because it was one of the service providers here in the US that had a major backbone meltdown when they added one more router. And the entire IBGP full mesh fell over. And they didn't have that many routers in the network either. And so it was a fairly major amount of work to try and get this network back and operational again. Okay, and it wasn't very many routers in the full mesh to cause the fallover. There were two solutions. The BGP confederation actually came first. That was the quick fix that was worked up in not very much time to basically get the service provider backbone running again. And then several months later, the other solution came along called the route reflector. What the confederation did was split the autonomous system into multiple ASs. So what it meant for this ISP is they could split the backbone into multiple regions, and then, so it looked as though the multiple regions were all different ISPs. They all appeared with each other, but where they talked to the outside world, they still all appeared as though they were in the one AS. So I say, there's a little bit of a hack to make the thing all work, and I still feel it's a little bit of a hack as well, which is why I don't really like teaching it that much, because people have a lot of trouble getting their heads around it. And you've got this sort of external, internal BGP and this EI-BGP thing and so forth, which for newcomers to BGP, it's quite a challenge if you want to scale. Whereas route reflector is much simpler to deploy and run. I mean, route reflector just uses one very, very simple concept in IBGP. Remember I said in IBGP that a BGP speaker will only pass on prefixes it introduces itself or learns from external speakers? Right, so for example, prefix comes into B, B will send it to A will send it to C. A will not send anything to C at all. So route reflector changes A. And what A then does says, if you learn prefixes from B, send them on to C. And you look at this and you go, well, why didn't they do this from the start? I have no idea. But this is the simple change that the route reflector makes. And then I often sort of think about this now, maybe I should just teach this right from the beginning as well. I've done an experiment once or twice, and then people forget how IBGP actually works properly, and you tend to completely break deployments of route reflectors as well. So I think it's important to understand how IBGP really works, and then learning how to scale it by using the route reflector technique. So that's it. It's pretty straightforward. It changes your network. You end up having something that looks like this. You have the core network like that. You've got the clients scattered around the outside. It kind of mirrors or nicely what a service provider backbone looks like. You've got your backbone transit area. Say you're talking OSPF speak, you've got area 0 in here. or your L2 network for ISIs, and then you've got the POPs sitting around the edge. It kind of fits nicely into that kind of structure. So the terminology, well, we've got route reflectors sitting in the middle here. Route reflectors are basically routers which have been configured to take IBGP prefixes and pass them on to other IBGP speakers. And then we've got clients. Clients speak only to the reflectors. They don't speak to anybody else at all. So all the clients have just one IBGP session with the route reflector itself. So rather, well, we've got what, 12 routers in the network here, so rather than having 11 IBGP sessions, most routers have got one. The route reflectors have got, well, one with each other, and then they've got one with each of their clients. So it really drastically simplifies how the IBGP mesh is set up. There are various rules about how prefixes are reflected. Prefix comes from a client, the reflector will send it to other clients, and it will send it to non-clients as well. You have the normal IBGP mesh between the reflectors, so normal IBGP behavior. So for example, if router B learns a prefix, it passes it on to A. A will not send the prefix to C. It'll only send the prefix to peers that are configured as clients. Okay? So you can have normal BGP speakers as well as clients hanging off a route reflector. So this is all described, updated RFC, RFC 4456, is updated RFC describing how route reflectors are implemented. You can fully mesh the clients if you want to. I mean, some ISPs, certainly those with large regional networks, multiple regions and so forth, like to do this because it means if they lose the connectivity to the core, the transit core, at least the regional network still works. And by regional network, I do mean some substantial network, multiple cities and so forth. Okay? You can have multiple hierarchies of this as well. I mean, you don't just, these can be route reflectors going further down the pole too. So this scales beautifully. You divide your backbone into multiple clusters. You've got at least one route reflector and a few clients per cluster. You need to fully mesh the route reflectors, of course. You can mesh the clients if you want to. It's no longer necessary. Hasn't been necessary for years. Please don't touch your interior routing protocol. Okay, I see some people who go major efforts of redesigning OSPF or ISIS, or people who decide, oh, I'm doing route reflectors now. Maybe I'll move from OSPF to ISIS as this will make them work better. It won't. All the IGPs are doing is getting connectivity to your router loopbacks. That's all they care about. So don't touch your IGP. If you want to do a IGP migration, do it at some other time, not the same time you deploy route reflectors. How we avoid loops? Well, we've got two new BGP attributes. We've got the originator ID, which is the originator of the prefix in the local AS. That's what the route reflector is creating. We've got the cluster list attribute, which looks a little bit like the AS path. So in other words, it records the route reflectors that the prefix has been bounced through. Okay? So that way you can tell where the prefix has gone through the network. And that's there to avoid any route reflector loops happening. Okay? So if a route reflector sees its cluster ID in the cluster list, then it won't accept the prefix. So we'll avoid having any route reflection loops. Multiple route reflectors can be configured in the same cluster. I mean, many years ago when these first appeared, this was strongly recommended. If you want redundancy, you must configure the route reflectors to be in the same cluster. Yeah, you can do that, but you have got to be very careful. Some people took this to heart. They converted their entire network into one route reflector cluster. So the route reflectors were sitting in different cities with topology in between them. Oh boy, did we end up with some fairly significant mess. So actually you find, generally my advice, and advice of a lot of people is, don't configure route reflectors to be in the same cluster. Make sure they're in different clusters. You can have clients, members of more than one cluster. That works just fine. Okay, so because all route reflectors in the cluster must have the same cluster ID, so you run into this cluster loop detection problem thing, and that catches a lot of ISPs out, a lot of ISPs. It's much easier to have different clusters, overlap them, clients peer with two different route reflectors. So it would look something like this. So a point of presence here, we've got cluster 1, so this is route reflector cluster 1, the green lines, route reflector cluster 2, the red lines. Okay? It's much easier doing it like this. I mean, the weird thing for us was, I mean, we did this from day one in our network, and it was only really when the Cisco Advanced Services guy came along to us and said, you can't do that, it doesn't work. And I went, what do you mean it doesn't work? We've been doing this for 2 years. Oh, So, and that's how we always achieved our redundancy, and that's pretty much the standard way of doing it. You don't end up with the problem of having potential loops. It's quite interesting. After I do this tutorial, and people look at it on the website or wherever, they come to me and say, oh, but I just do use the same cluster ID and it works fine. It's like, that's okay, because you understand what you're doing, you've configured it properly, and there is no problem. I mean, if these two routers in the same POP, it's okay. It's generally fine, because they've got just a bit of wire joining them, or a bit of optics joining them. But I've seen many deployments where this is in city number 1, that is in city number 2, and there's significant infrastructure, including routers sitting in between them. And these two routers have the same cluster ID. And you've got partition in the network, and it just causes the whole network to fall to pieces. I've fixed more than enough of these in my time that I really don't want to fix anymore. So that's why I'm always advising this. If you're new to this, try and do it this way, because you really won't end up in any trouble. So, Route Reflector solves the IBGP mesh scaling issues, doesn't touch packet forwarding, it's only a way of distributing prefixes around the backbone. Normal BGP speakers coexist. If your implementation doesn't support route reflectors, well, A, I think that's pretty serious. B, it's only the ones that need to know how to handle the route reflector clients that really matter. It's very, very easy to migrate to these. Very easy. Where you want to replace them, try and follow the physical topology. That's pretty important. Right, don't put two route reflectors in one rack, in one point of presence, off the same UPS in one part of the country, just to serve the entire rest of the country. It's probably not going to scale awfully well, even though I still see some designs out in the world to try and do this. They've got two route reflectors for the entire backbone. Well, because that's what such and such said to do. Think about it. Think what breaks. If your UPS stopped working, you'd lose your entire IBGP and nothing would work. So try and follow the physical topology. The way I like to do it is a route reflector cluster in each point of presence. And then you just simply fully mesh the backbone as you would normally do. Route reflector cluster in each POP, and things work pretty well. Typical service-powered network, two core routers, the route reflectors, two overlaid clusters. You can do further hierarchy if the core mesh is too big. You may have a backbone, then you can do regional network, and then you can have another layer of route reflectors as well. I've seen 3, 4 layers. I haven't seen more than 4 layers happening, but 3 is reasonably common. Split the backbone into regions and set up the clusters working that way. And then when you want to do the migration, well, I mean, a colleague and I were foolish when we did this in '96 because we just did the whole thing in a 2-hour maintenance slot, and it was all just fine for our 70 or so routers. Yeah, try not to do that. I mean, try and just work on one POP at a time and get happy with it, comfortable, and then maybe come back a week later and do the next one and so forth. It's just, better for peace of mind and stress, especially at 4 o'clock in the morning or whenever your maintenance is. Okay, so something like this, pick on a corner of the network, set up your clients, route reflector, remove the redundant IBGP sessions, and then you're good to go. So it's pretty straightforward to do. So that's really all there is about route reflectors. As I say, the slides will have BGP confederations in the handout. I'm not covering them in the presentation here. So after the break, we're going to look at route flap damping. So let's have a break. It's all nice in here. I want to try and start again at 4 o'clock. So that's only 20 minutes.